Hello, hello. Yeah. So today I'm doing fine. How are you guys? Stressed for this midterm, this week's midterm?
Yeah.
Yeah. Let's see. Hello, hello. Okay, so I'm gonna go over some 118A acid-base stuff, and then we can move on to the 118C stuff because I know you guys have a midterm this Thursday. Yeah, right. So this question here is asking to use curve arrow notation to show electron flow in each of the following reactions and draw the structure of the product. So whenever you see a Cl, right, think, or no, not whenever, like it's not all the time. When you see HSO3, that's gonna have a negative charge right there. So that's gonna be our base, right? Because our base is going to um, have electrons to attack a proton. Wait, actually, this is gonna be neutral. If I draw out the Lewis structure of this, HSO. Actually, yeah. So this chlorine here is not a spectrated ion. It's gonna be neutral with this HSO3Cl, meaning that this hydrogen right here attached to the S is our acid. And when you see an amine with a pair of electrons, this amine here with the pair of electrons is going to be basic, right? So when we draw acid-base reaction arrows, the lone pair of electrons on nitrogen is going to attack the hydrogen, and the bond between the sulfur and hydrogen is going to break and go into the sulfur right there. Yeah, so this is 118A. This is 118A farahat. Acid-base practice, not 118C, right? And when that happens, this nitrogen here gained a bond to hydrogen, which gives that nitrogen a positive charge. Do you understand why this nitrogen has a positive charge now once it has the fourth bond to hydrogen?
Because it has an extra pair of electrons.
Um, not
Or no.
extra pair of electrons. It lost the pair of
Yeah.
electrons. It has an extra bond, right? Because this nitrogen is now bonded to 3 hydrogens. So if I were to draw out the bonds to hydrogen like this, 1, 2, 3, this nitrogen here has 1, 2, 3, 4 electrons to itself. But nitrogen is on the 5th column or 5th group of the periodic table, so it wants 5 electrons. It has 5 valence electrons, but it has 4 electrons to itself right now, so that's gonna have a +1 charge like that, right? And then sulfur here, it gained a pair of electrons, so this is going to be negatively charged. Right, because sulfur is on the 6th column of the periodic table, so it wants 6 electrons to itself. But right now we see it has 1, 2, 3, 4, 5, 6, 7 electrons. 6 minus 7, negative charge. Does that make sense? Like how I drew out these arrows? 2 arrows happened here. This pair of electrons attack this hydrogen, making a new bond between this nitrogen and hydrogen, right? This new bond right here has 2 electrons. Those 2 electrons are coming from that pair of electrons right there. And then at the same time, as this hydrogen here is making a bond with that nitrogen, the bond between the sulfur and hydrogen is breaking and going onto the sulfur to give that sulfur a pair of electrons. There. Did that make sense?
Yeah.
Yeah. Yeah, this is not 118C. This is 118A. Okay, so how would you predict the product for the next one here? Like, I mean, how would you draw the arrows out for this one?
Would you take the lone pair from nitrogen
Mhm.
to get the hydrogen?
Yep. Get the hydrogen, and then another arrow has to happen as well. The bond between the hydrogen and iodine is going to break and go onto the iodine like that. Right? And that's going to give us these products here. Right? Did that make sense or any confusion?
That makes sense.
Now, the next one here is a little bit trickier, right? Because this will come back in 118C as well. If you have two competing bases and one equivalent of acid, then you are going to choose the stronger base to get protonated. Which group do you think is going to be more basic, the amine or the alcohol?
Is the most basic the weakest acid?
You could think of it like that. The most basic is going to be the weakest acid.
So would it be nitrogen?
Yep, it would be nitrogen. But the way that I like to think about it is the electronegativity difference between nitrogen and oxygen. Nitrogen is less electronegative than oxygen, so it's more willing to give up its electrons, right? More willing to donate its electrons, whereas oxygen is more electronegative than nitrogen, so it wants to keep its electrons. It doesn't want to attack a hydrogen. It doesn't want to give it up, right? So nitrogen is going to be more basic because it is less electronegative than oxygen, meaning that it's willing to give up a pair of electrons and attack the hydrogen like that, right? Or you could think of it like stronger acid, weak base as well, but that's not always the case, right? But in this case, it worked out, right? And that's going to give us these products here. Did that make sense?
Yeah.
H and then CO minus. Okay. Try out the rest and then let me know if something doesn't make sense, and I'll move on to 118C because there's a lot of people here from 118C.
Okay, thank you.
Yeah, and then I'll get back to you. Let me know if you have any questions on these practice problems.
Okay.
Yeah. Yes. Jillian, you had a question?
Yeah, can you just quickly go through um like a basicity problem, like in terms of like amines, like what makes like it more, there was like a question on Mariah's practice. It was like what makes something more basic than the others.
Right. And there's two different conditions that the basicity of amines can fall under: the gas phase or aqueous solution. Right. So the gas phase is going to be easier to think about because I'm going to give up the ranking list of the basicity of amines like this. Ammonia is going to be the weakest base, and then it's going to be the primary amine, and then it's going to be the secondary amine, and then it's going to be the tertiary amine, right? Going from left to right is increasing in basicity, right? This tertiary amine here is the most basic compared to all these other amines in gas phase. Right? That's the important scenario. And the factor that determines this basicity is the amount of R groups attached to the nitrogen, right? And in 118b, we learned that R groups are EDGs, electron donating groups, by induction, right? So they're just going to naturally donate electrons into the nitrogen like that, right? And because this tertiary amine here has the most amount of EDGs, R groups, this nitrogen here is gaining a lot of electrons, right? Making it very basic. Whereas if we look at the other extreme, this ammonia here has no EDGs attached to it, no R groups attached to it, right? So if there's no R groups attached to it, EDGs attached to it, it's the weakest base. Primary has only one R group, secondary has two R groups, right? So that's the most straightforward scenario in gas phase because all we have to worry about is the amount of R groups attached to the nitrogen, right? It gets a little bit trickier when we move on to aqueous solution. So in aqueous solution, we have to worry about three different things. And I'll show you what that is, but I'm just gonna first give you the ranking list where ammonia is the weakest base, and then tertiary amine is the second weakest base, and then primary amine, and then secondary amine. Right. So going from left to right here in aqueous solution is increasing in basicity. Basicity. Now we see that the tertiary amine here is in between the ammonia and primary amine, which is weird, right? Because we expect it to be after the secondary amine, since it has the most amount of R groups, most amount of EDGs attached to it. So to explain this, I'm going to draw out the conjugate base. I mean, conjugate acids of these, right? Conjugate acids. So let's say some kind of acid is in the solution, protonating all of these amines. When we protonate all of these amines, we are going to get these conjugate acids here. Right, where all of these nitrogens will have a positive charge now. Right. So now, in aqueous solution, that means that our environment has water or alcohol, some sort of product solvent, right? Let's say we had water in the environment. We know that oxygen is more electronegative than hydrogen, so oxygen is going to be partial negative charge, hydrogen is going to be partial positive charge. So now the partial negative charge oxygen here, there's a lot of them. Like there's a lot of them in the environment. They're going to surround the positively charged nitrogen, right? So think of these oxygens here as the oxygens of water. I'm not going to draw out the hydrogens, but these are the partial negatively charged oxygens wrapping around the positive charged nitrogen. And this is what we call the solvent shell or solvation shell, right? And this solvation shell here stabilizes the positive charge. It makes it more stable. It's supporting that charge. If we look at the tertiary amine here, these R groups here are increasing steric hindrance, so that disrupts the solvent shell, right? The oxygens are not able to wrap around this positive charge because of the steric hindrance of the R groups. So there's two factors that explain why tertiary amines are less basic than primary or secondary amines. And the first factor that I just talked about is that their steric hindrance disrupts the solvent shell. Right? And if there's a weaker solvent shell, then this positive charge is less stable. And if this is a less stable conjugate acid, it means that it is a weaker base. The reason why the tertiary ammonium ion is more stable than the ammonia is because of the R groups. Right? The R groups are like donating electrons into the positive charge, making them stabilize. So this right here is increasing order of stability of conjugate acids. Right? The primary amine has less steric hindrance, so they can have a tight solvation shell, and the secondary ammonium ion also has a tight solvation shell. They don't have that much steric hindrance. The other factor that you need to know is that the tertiary amine has less H bonds. Right? We see that this tertiary ammonium ion here only has one bond to hydrogen, so that makes them able to do only one H bond, right? Whereas this nitrogen here has three bonds to hydrogen, so they could do more H bonds. The more H bonds a molecule can do, the more intermolecular forces they have, and the more they can be stabilized, right? So these two factors here, they're going to counteract the EDG induction effect, which explains why the tertiary amine is less basic than primary and secondary amines in aqueous solution. That's the important scenario in aqueous solution, right? In gas phase, then it's more straightforward. The more R groups the amine has, the more basic it's going to be, right? We don't have to worry about any solvent shell because there's no aqueous environment. There's no product solvent around, right? There's no partial charges to worry about. But in aqueous solution, since there's a product solvent, we have to worry about solvent shells, right? Which changes up the ranking of bases for amines. Right. Did that make sense?
Yeah, it does.
Yeah.
But what if there's like a benzene attached to the amine?
Oh, so yeah. So that's gonna talk about some other concept. Like I think you're talking about chapter 20 practice problem, right? Or like if you're ranking the base of amines, or chapter 21 actually, chapter 21 right here. Yeah, that's actually another tricky concept. So let's go over that, and then let's go over chapter 21 reactions, and then the charts for chapter 19 and 20. That would help you guys figure this out here. Right. Let's see, chapter 21. No, that's way too far. Chapter 21's up here somewhere. Manic. Water. This is chapter 20. Chapter 20.
I think you just passed it. It's a
Oh,
decreasing basicity.
decreasing basicity. Manic. Over here. Okay. Yes. So when they are asking for the decreasing basicity, the most basic on the left, what I think about is the pair of electrons. So I'm going to compare the pair of electrons on these nitrogen atoms here. Right. The less stable the pair of electrons, the more reactive they are, meaning the more basic they are. Right. So automatically, I see that this pair of electrons here is the least basic because it cannot do any resonance at all. Right. And because it's the least stable, it's going to be the most reactive, making it the most basic. So this is our best base here. Right. Now, if we compare these two pairs of electrons right here, this pair of electrons can do resonance with the carbonyl like that. And this pair of electrons can do resonance with the benzene like this. So you might be thinking that this pair of electrons here is more stable because it has more resonance structures, right? It can do more resonance. It's more delocalized. Whereas this one can only do like one resonance structure, making it less stable. But the tricky concept here to keep in mind is that we do not want to break aromaticity. Right. So this benzene here doesn't really want to do resonance with the pair of electrons on this nitrogen, right? So that prevents this lone pair of electrons from doing resonance because we're going to turn this aromatic molecule into a non-aromatic molecule, and that's like unstable. So resonance is able to happen here like more readily than this structure, right? So if that's the case, this structure here is going to be like this pair of electrons here is less stable than this pair of electrons because even though it looks like it can do more resonance, it can like do less resonance, right? Because the benzene is like saying no, I don't want to break the aromatic structure. So this is going to be the second most basic, and this is going to be the least basic because this pair of electrons right here is the most stable, right? So the answer here should be Z first, and then X, and then Y. Right. The tricky concept here is that they do not want to break aromaticity, right? Which should be answer A.
Thank you. That makes so much sense.
Yeah, no problem. Okay, so let's finish chapter 21 reactions. But before we do that, I realized that there was a mistake that I said in last office hours for that synthesis round I did, right? Which was this right here. So last night I gave you guys the synthesis round to try out. right? And someone asked why can't we do reduction of nitrile to get this right here? And the reason why we can't do that is because let's say like we had the amide right away, right? Like I'm just gonna skip a lot of steps here, but let's say we had that nitrile here, right? And if we reduce this nitrile with lithium aluminum hydride and an acid workup, we still have that extra carbon right there, where that carbon is the carbon of the nitrile, right? But we want to remove that carbon. We want to take away the carbon. And the hallmark reaction that does that is Hoffman rearrangement, right? So you could use either one of the two synthetic routes we like came up with last night that used Hoffman rearrangement. We need Hoffman rearrangement somewhere in the synthesis for this to work, right? We can't make this in nitrile because the nitrile still has like that carbon right there. And this would be the answer instead if we reduce the nitrile. But we don't want that carbon. We want to get rid of that carbon, which makes us do Hoffman rearrangement. So benzene ring doesn't want to break aromaticity. That's why it's not basic. Yeah. So because the benzene here doesn't want to break aromaticity, the lone pair of electrons here cannot do resonance with the benzene. Think of it like that, right? Like the benzene is saying, no, I don't want to do resonance. So that makes this lone pair of electrons less stable, more reactive. So it's actually making it more basic, more reactive than this one here. Right. But it's still more, like this pair of electrons here is still more stable than the one that has like no chance of resonance at all. Like there's nowhere to go for resonance here for this pair of electrons. Right. Okay. So chapter 21, I think we left off with Hoffman elimination. Which is going to have two reagents on the arrow. The first step you're going to see is CH3I excess, and you might see some kind of base like I forgot what the base was. Yeah, but some kind of base. Second step, Ag2O, H2O, and heat. Right. The first reaction of this Hoffman elimination overall reaction is going to be over alkylation of the amine. The second reaction of this is going to be Hoffman E2. So you're gonna make the less stable double bond here. So I'm gonna give you guys a simple example. Let's say we have this amine right here. And I have these two reagents. The first step is going to be CH3I excess. Second step is going to be Ag2O, H2O heat, right? So the first step is going to have this amine act as a nucleophile, attack the CH3, kick out the I for SN2 reaction. When that happens, we're going to have this intermediate right here, where this nitrogen is positively charged, right? But the base that we have in the reagent is going to come in, deprotonate and neutralize the nitrogen to give it a pair of electrons. Right. And when it gained a pair of electrons, it's going to be a nucleophile again and attack another CH3I to get this intermediate. And we keep going until we can no longer deprotonate or neutralize the nitrogen, right? So this nitrogen here is still nucleophilic. So we're going to attack another CH3I, keep going. And at this point right here, we can no longer deprotonate or neutralize the positive charge. So what we do is that we think of this as the good leaving group now. Like one of it is going to be the good leaving group, but think of that as a good leaving group. Locate the alpha carbon, which is the first carbon attached to that leaving group, and then locate your beta carbons, which is one carbon away from the alpha carbon, right? So if we want to look for the Hofmann E2 reaction, we want to make the less stable alkene. Which hydrogen would we have to deprotonate? Hydrogen A or hydrogen B? If we want to make the so A is the usual hydrogen like you think of when you want to make the more stable alkene, right? But that's the Zaitsev product. The Zaitsev alkene. For Hofmann elimination, we're looking for the less stable alkene, which is the less substituted beta hydrogen. Right. So the less stable or less substituted beta hydrogen is hydrogen B. We grab that hydrogen, we make a double bond here, and we kick out that good leaving group right there. So those three arrows will happen at the same time, right? So be careful of this reaction. When you think of Hofmann, think of the less substituted alkene, the less stable alkene, right? And that's going to give us this less substituted alkene here, this key for the Hofmann elimination, and water. And in all Hofmann elimination reactions, you know that you'll get to the final answer if you have this as part of your answer, right? This trimethylamine. That trimethylamine, or you might sometimes see it as like a quaternary over-methylated amine, then you know that you are finished with the reaction, right? So any questions on this before I give you another example that is going to be a little bit trickier? Okay, so let's look at a trickier example where I have this ring right here, right? And I react it with the Hofmann elimination reagents. First step, CH3I excess with the base. Second step, Ag2O, H2O heat. I'm going to show you guys the shortcut of how to predict a product quickly without having to do the whole mechanism, right? To save time on the exam. So what you guys do first is that know that in the first step, our goal is to over-methylate or over-alkylate the nitrogen to give it positive charge, right? So once that nitrogen gains a positive charge and it can no longer get deprotonated, this is when we move on to the second step and do Hofmann E2 reaction. I first locate my alpha carbons. So these are the alpha carbons here, the first carbon attached to the nitrogen. Then I find my beta carbons, which is a carbon away from the alpha carbon, right? And then I draw out at least one beta hydrogen for all beta carbons. And then from this point right here, I choose my least substituted hydrogen, beta hydrogen, for the Hofmann product, E2 product, right? So that's going to be this left one right here. This is primary, whereas this is secondary, and this is tertiary, right? Once I grab that hydrogen, I'm going to make a double bond here and kick out that leaving group like that. And that's going to give me these products here, right? But this is not my final answer. I do not stop here, right? Because I do not have my key yet, right? The key of the trimethylamine. So that means I have to keep going. This nitrogen right here is nucleophilic, which can attack another CH3I, kick out the leaving group, and yeah, I told you guys I'm not going to do the mechanism to show you guys the shortcut on how to predict the product. So you guys know that we're going to over-methylate the nitrogen again, giving it a positive charge. And then at this point right here, we do the same process. Locate your alpha carbons, and then after that, locate your beta carbons. And then from here, choose the least substituted beta hydrogen, which is the one on the bottom. grab that, make a double bond here, and then kick out that leaving group, right? And that's going to give us this product here, right? But we're not finished yet, right? We don't have the key yet. We don't have the trimethylamine. So we're going to over-methylate that nitrogen again and find the alpha carbon, find the beta carbon. There's now only one beta carbon to deprotonate, which is this one. Grab that hydrogen, make that double bond there, kick out that leaving group or key to give us this product here. The key to stop the reaction. And these alkenes right here. Right, so for Hoffman elimination, these are our 3 products that we formed. Now, right. So that's how you can predict the product for Hoffman elimination quickly without doing the whole mechanism. Yeah, so it's like if you guys watched Attack on Titan, we don't stop the reaction, we keep going until we find the key to the basement. Right, I don't know if that makes sense, but right.
Brian, I have a quick question.
Yeah,
Between the first step, so the black structure to the first red structure,
yeah.
did you add an extra methyl to the nitrogen there when you were pulling it off after the E2?
Right. So when I grab this beta hydrogen right here and make a double bond right here, and this bond right here, when it breaks and goes onto the nitrogen, it is supposed to be neutral with no positive charge, like that.
Oh, so
Right.
it's not supposed to be in lone pair there?
There is supposed to be a lone pair here, which makes it nucleophilic. And I just use that lone pair to attack another CH3I to kick it out, which is why you see another methyl group here.
I see. Okay, so you just get that intermediate step.
Right.
Gotcha.
I just skip straight to that point. I'm not drawing the whole mechanism here, just to save you guys time on the exam, and predict the product quickly. Right.
Okay, cool. Thank you.
Yeah. Right, because we want to get to this point right here of the trimethylamine. Yeah. Okay, so that's Hoffman elimination. Let's move on to manic reaction, which is probably the biggest, most involved reaction in chapter 21. Manic reaction. So now this is a 3-component reaction where I'm gonna like generalize everything at the beginning and then give you specifics later on and how to like predict the product more quickly. So you're going to have a more reactive carbonyl plus one of these amines, ammonia primary or secondary amine, plus a less reactive amine in acidic conditions. So you can have like a pH of 3 to 4. You might even see HCl. Second step, but that's it. Yeah, just acidic conditions. And the product for manic reaction is always going to be a beta amino carbonyl. Wait, and I'll show you what that is when I go over the specifics. And that's how you can check if you have the right answer or not, by checking if you have a beta amino carbonyl. Okay. So before I go over that, let's review what I mean by more reactive versus less reactive carbonyl. If I give you guys these 3 carbonyls here, like aldehydes and ketones, do you guys know which one would be the most reactive? This is a review from 118B right here. Yeah, which carbonyl would be the most reactive, and why?
Formic acid, because it doesn't have those electron donating groups.
Yep, this one right here, form aldehyde, because it does not have the R groups, the electron donating groups. Right. This carbonyl carbon here of the formaldehyde has the biggest positive charge, whereas this carbonyl carbon of the ketone with 2 R groups donating electrons into it has the smallest positive charge. Right. So that's what I mean by more reactive carbonyl versus less reactive carbonyl. For example, if I have this aldehyde plus this amine plus this ketone in like some acidic condition, we're going to form a beta aminocarbonyl, right? But the more reactive carbonyl and amine are going to come together to form an imine, right? Or if it's a secondary one, it could be enamine. Actually, no. It's still going to be iminium ion. Yeah. So it's going to be iminium ion that's going to be formed from the more reactive and more reactive carbonyl and the amine to form the iminium ion. And then the less reactive, oh, this is supposed to be carbonyl, less reactive carbonyl. Less reactive carbonyl. The less reactive carbonyl is going to form our enol, right? Where the enol is the nucleophile, the iminium ion is the electrophile. They come together, like nucleophile, like electrophile, to form the beta amino carbonyl, right? So this is my more reactive carbonyl. This is my less reactive carbonyl. Combining my more reactive carbonyl and amine together, I am going to have this iminium ion here, right? And this is a 118B mechanism when we react a aldehyde or ketone with an amine in acidic conditions, we're gonna have the iminium ion, right? This dot right here is gonna be my electrophile, and this is going to be my enol here from my less reactive carbonyl, like that, right? And the alpha carbon of my enol is going to be the nucleophile, right? So you can start that as the nucleophile, and this is my dot. So the enol is going to attack the electrophile, the iminium ion, by reforming the carbonyl, having the star attack the dot, and pushing the double bond onto the nitrogen like that, right? And then when that happens, we are going to have this right here. So I'm just going to draw out the star, new bond between star and dot. The star is attached to a methyl, which is this methyl. The dot is attached to ethyl, and this nitrogen amine right here, right? So this will get deprotonated and this will get protonated because we are still in acidic conditions, right? So in acidic conditions still, this nitrogen here is still going to get protonated, positive charge. It's going to get neutralized once you add base to it for a base workup step, right? And this is what I mean by beta aminocarbonyl. This is your carbonyl carbon. This is your alpha carbon. This is your beta carbon. And at the beta carbon, you have an amino group attached to it. So this is what we call a beta amino carbonyl, right? Because beta to the carbonyl, there's an amino group. So let me show you guys another example here, right? Let's say we have that in acidic conditions. When you see CH2O, this is going to be your formaldehyde, right? So instead of like forming your iminium ion and combining your more reactive carbonyl with amine, there's a quicker way to predict the product for this manic reaction, right? first you have to determine that you do have a manic reaction in the first place. And to do that, you have to recognize your three components: the more reactive carbonyl, the amine, the less reactive carbonyl, and the acid, the acidic conditions, right? Once you figure those reagents out for manic reaction, then you could do this trick to predict the product quickly. At the less reactive carbonyl, star the alpha carbon. That's going to be your nucleophile. At the more reactive carbonyl, dot the carbonyl carbon, right? That's going to be your electrophile. The carbonyl is going to disappear. The carbon double bond oxygen is going to disappear in the product, right? So let's combine these two together right now. This is my star. This is a new bond between the star and dot, right? This dot right here is attached to two hydrogens. You can leave that out, it's invisible in the product, but I'm going to draw it out just to make it more clear of what's going on here. And the carbonyl, I said earlier, it just goes away. It disappears in the mechanism, right? And then to finish the product, connect the amine to the dot minus one hydrogen. Like that, right? This is the amine right here that connected to this dot minus one hydrogen. It does not have that hydrogen anymore, like that. Right? And this is our beta aminocarbonyl. And that's how we can make sure that we have the right answer. Like that. Yeah, let's do one more example. And I want you guys to try it and let me know what you guys get for this.
What are the side products? Is it is water released?
Yeah, water is released as a side product, where water is the oxygen of water is coming from this carbonyl right here. Right. Water is released from that carbonyl. Skip. This becomes water. Yeah. I'm gonna give you guys the three components in different orders, and I want you guys to determine what is what. Okay. Given these three reactants in acidic conditions, predict the product. Right. I forgot to mention as well, I noticed this for Farahat's Achieve homework and practice problems. If you are still in acidic conditions, you're going to have this amine protonated still in this protonated form with a positive charge, right? Unless you have a base workup, like first step is acid, second step is like some kind of base like NaOH or KOH, that can be neutralized. But if this is still in acidic conditions, the amine is going to stay protonated with a positive charge, right? Okay. Try this, and then we'll move on to nitrosation of amines with primary amines, secondary amines, and tertiary amines. And then I'll give you guys a lot of synthesis problems to practice with the reactions. Okay. Yes. Let me know what you did. How'd you do it? Let's see. Third reagent is the less reactive carbonyl. Second reagent is the more reactive carbonyl. And then this is the amine. Nice. Okay. So once we figure that out, star the alpha carbon of the less reactive carbonyl, dot the carbonyl carbon of the more reactive carbonyl, get rid of the carbonyl, carbon number 1 oxygen, combine the two together. So if I want to do that, I'm going to do this. Rotate my turbo up here. This is my star. This is my dot. That's the new bond between them. This dot right here is attached to a phenyl group, benzene, and a hydrogen, but I'm going to leave that hydrogen as invisible. And I'm just going to connect that dot with the amine minus 1 hydrogen to give me my manic base, or beta amino carbonyl. Right, so that's a quick way to predict the product without doing the whole mechanism. Yeah, so if you guys are getting confused on this, on how this is getting connected, I'm gonna show you guys the step-by-step mechanism, just to give you guys more context of what's going on here, right? But this is the quick way to do it on the exam to save time. Yes, Sinyan?
So should we get rid of the H if we were only in acidic conditions, or we just leave it like?
Right. Yeah, so if we're in acidic conditions, I forgot, the H is gonna stay there. I'm used to getting rid of the H because other professors give the manic product as a neutral product, but for farahat, the H stays there in acidic conditions, positive charge.
Okay.
Yeah.
And also, is like the ketone always symmetrical?
Yes, the ketone is always going to be symmetrical for testing purposes, unless he wants to be mean and makes it asymmetrical. And if it's asymmetrical, then you're going to get mixed products, right? Like if this was like
Okay.
a methyl group there, then you have to draw 2 different manic products. Yeah.
Okay, that makes sense.
Yeah,
Thank you.
but yeah, no problem. Okay, so let me show you guys the step-by-step mechanism. The first step is iminium ion formation. The second step is going to be enol formation, right? And then the third step is going to have the enol plus the iminium ion together. They're going to react together to get your beta amino carbonyl, right? So let's look at this case here. Say we have this aldehyde, this amine, and this ketone, right? Acidic conditions. So the first step, form the iminium ion. Right? Usually professors protonate the carbonyl oxygen of the more reactive carbonyl. But based on what we talked about last night, if we are in acidic conditions, which group do you think is going to get protonated? Which group do you think is the best base that will get protonated in acidic conditions?
Would it be the amine?
Yep, it would be the amine, right? The NH2, because the nitrogen here is a better base than the oxygen since it's less electronegative. So the amine is going to get protonated by the acidic conditions to give us this positive charge proton source now. And this proton source here is going to protonate the more reactive carbonyl, right? The more reactive carbonyl oxygen is going to get protonated by this amine here to give me this activated carbonyl. Right. Once this carbonyl is activated, the neutral amine that left as a result is going to attack this activated carbonyl, pop the double bond onto the oxygen to give me this tetrahedral intermediate here. I'm gonna draw it down here. H, nitrogen, 2, H plus. Now, once we have the tetrahedral intermediate, this is where I do my proton transfer step, where I deprotonate the group that I want to keep and protonate the group I want to kick out. So I'm gonna do that by using another amine, because we have a lot of amine in excess in the environment. To deprotonate that, this is my best base in the solution right now, okay. Which makes it neutral, bad leaving group. And I'm gonna use the protonated amine as a proton source to protonate the OH and make it into a good leaving group. So this is iminium ion formation here. Once everything is primed and ready to go, we drive off the good leaving group by forming the iminium ion and kicking off that good leaving group right there, giving us this iminium ion here. Right. Now, once we have this iminium ion, we're done with the first step. Right, that's our iminium ion. Our second step of the mechanism is to form the enol. And that's going to come from the less reactive carbonyl, like this. Right. And in acidic conditions, this less reactive carbonyl is going to get protonated, give us this protonated carbonyl with a positive charge. And then our best base source is going to deprotonate that beta alpha hydrogen, make a double bond there, push the double bond onto oxygen, and form our enol. And that's it for the second step. Right. Now we have our enol here. Once we have the enol, we move on to the last step of the mechanism, where we bring the enol and iminium ion that we formed in the first step together to react and form the beta amino carbonyl. Right. So this is the enol that we formed in the second step. This is the, what was the iminium ion? This is the iminium ion that we formed in the first step. Right. My nucleophile is going to be the alpha carbon of the enol, the star here. My electrophile is going to be the iminium carbon, that dot right there. So I'm going to reform the carbonyl between the carbon and oxygen, have my star attack the dot, pop the double bond onto the nitrogen, and connect those two together. Right, this oxygen bonded to hydrogen, positive charge, star, new bond between star and dot. This dot is now attached to a methyl, which is this methyl here, a hydrogen. I'm going to leave that as invisible. And it used to be double bonded to a nitrogen, but it's now single bonded to a nitrogen with a ethyl group and a hydrogen, right? And then I'm going to kill two birds in one stone here. I'm going to deprotonate this group and protonate this group in one step, right? I'm going to do it intramolecularly like this. And this is for farahat especially. If you stay in acidic conditions, this will be your final answer. Where you, oh, that's too many carbons. Where you have a positively charged nitrogen at the beta carbon, right? Beta amino carbonyl, right? Where you see that the star here used to be, is actually the alpha carbon of the less reactive carbonyl. The dot here, right? The dot here is the carbonyl carbon of the more reactive carbonyl, right? Of the iminium ion. And we see that the carbonyl, it left as water right here, right? That's the side product. Like Peter said earlier, water is the side product that gets kicked out in the mechanism, which is why we don't see the carbonyl there anymore. And the amine just connects to the dot like that. So this is the whole like complete mechanism, which I did not recommend doing if he gives you predict the product problem. Like I recommend like doing the shortcut to save time. If you have time, then you could do it if it helps you, but I don't recommend doing the whole mechanism if it's predict the product. Right. Yeah, let me zoom out. Okay, guys. So first step, form the iminium ion by reacting the more reactive carbonyl with the amine in acidic conditions. 118B reaction here. Second step, also 118B, form the eno, tautomerized into the less stable tautomer. And then bring in the products of like steps 1 and 2, the eno and iminium ion, react them together to make the beta aminocarbonyl, aka the manic base, the product of the manic reaction. Like that. Okay. There is a way to go backwards retrosynthetically, like if he gives you a manic base or beta aminocarbonyl and how to break that down into the 3 different components, but I don't know if he's going to include that for the synthesis. But let's go over the nitrosation of amines now, right? So nitrosation, and then let's end up with another synthesis problem, nitrosation of amine. So you could either have a primary amine, a secondary amine, or a tertiary amine, and you're gonna react with these reagents here: NaNO2, HCl. Same for all of these, right? Primary, secondary, and tertiary. If you have a primary amine, you're going to have this diazonium salt, right? On multiple choice, you might see it as this in blue, N2Cl. If you have a secondary amine, you're going to have this nitrosamine, right? And you might see it in this form, which is the same thing, right? The end of one O is NO. If you have a tertiary amine, you could have the nitrosamine ion, nitrosamonium ion, like that, and you might see it in this form, positive charge on that nitrogen, right? And these nitrosamines, a conceptual thing like you need to know is that they are carcinogenic. Right. Okay. Are you guys ready for a synthesis problem? I could try to involve chapter 19, 20, 21 reactions here. Yes, know these for predicted products. Know these reactions for predicted products, and know the difference secondary amine and tertiary amine and what they make, and recognize the reagents for this reaction. Yeah. Don't worry about the mechanism. Yeah, don't worry about the mechanism. For the mechanism, worry about chapter 19 and 20. Nucleophilic acyl substitution, like hydrolysis, Fischer esterification, esterification. Know which derivatives need acid, base, or heat, and know the intramolecular reactions as well, like how to form bonds, how to break bonds apart, like how to recognize when you have an intramolecular reaction. Right. Okay. Let's do a synthesis problem with chapters 19, 20, 21 reactions. Ooh, I want to do this one. Let's do this. Wait, no. actually. Okay. One more. No, that's gonna do too much. Okay, try this synthesis problem for now, and then I'll create another one that I wanted to use as well. But then if I do that here, it's gonna like cause problems. So I'm gonna make that separate. But try the synthesis here, right? Converting that to that. Okay, yeah, let's do these two, and that should be good for. Wait, no, let me make this longer. No. Okay. Chapter 19, 2021. Okay. Would this be an intramolecular reaction after doing organometallic or CN to add carbons, then oxidizing? Yes. So this first synthesis here will involve an intramolecular reaction and an organometallic or CN to add carbons and oxidizing. For the last step of the first one, yep, carboxylic acid, alcohol, ester, and that's going to be Fischer esterification. Yep. But I'll get back to you. I'm going to point something out, what you just said. But let's see. For the last step of the first one, do we need to add base to make a better nucleophile out of the OH or heat, or neither? Yeah, so for the last step right here, if we see an ester being formed, right? Someone says we're that this is gonna be a carboxylic, right? A carboxylic acid and then reacting together. That is esterification. And in Fischer esterification, it could only work in one conditions. It only works in acidic conditions. It never works in basic conditions. And can anyone tell me why it never works in basic conditions? Right? Like imagine you put some base in the solution of a carboxylic acid. What would happen? What is one of the fastest reactions in OChem?
It'll be an acid-base reaction instead of the esterification.
Yeah, right. That's why Fischer esterification cannot happen in basic conditions, because the basic conditions is going to do an acid-base reaction instead, forming the carboxylate. So we want to use acid and heat. The alcohol is already present here, right? So going back to what you said earlier, we want to increase this carbon skeleton by 1 carbon, and there's 2 methods that we can do to do that. We could either do the organometallic way, like MgBr and then carbon dioxide way, or the nitrile way, right? Based on what we have in the starting material here, which method, which strategy do you guys think is best to do? The organometallic route or the nitrile route?
Organometallic.
Yeah, so organometallic, right, is going to be a strong base, strong nucleophile. If we were to do an organometallic Grignard, like Mg ether, to create this Grignard reagent right here, this Grignard reagent right here, that carbon is a very strong base, very strong nucleophile. And when it detects an acid present, it's going to deprotonate that acid right away before attacking a carbon dioxide. Like before we even try to add a carbon dioxide here, it cannot attack that carbon dioxide because it's distracted by the acid. Right? Acid-base reaction is going to happen faster. So we can't do a Grignard reagent here. What we have to do is hydrolysis of nitrile, right? Where the first step is to do SN2 reaction, substitute the Br with the Cn, and then we do hydrolysis of the nitrile with acid, water, and heat to get the carboxylic acid. And then from this carboxylic acid to the final product, we use acid and heat. Intramolecular Fischer esterification. Right, intramolecular because the nucleophile is on the same molecule as the electrophile, forming a ring. And this is Fischer esterification because the components of Fischer esterification is a carboxylic acid and an alcohol, which we do have here, a carboxylic acid, alcohol, forming an ester. And this is a cyclic ester or lactone because it's intramolecular, right? And we have to put acid or heat because it can only happen in acid or heat and heat conditions. Yeah, so the Grignard here was a problem because of the acid present. If we have something like this, however, right, we cannot do the nitrile route, no reaction, right? Because we want to do SN2. This substrate here is too sterically hindered, right? So what we have to do instead is the Grignard route, organometallic route, right, to get to this carboxylic acid. So that's the limitation for nitrile. This is the limitation for organometallic. Yeah, so it looks like you have to use organometallic because you see the bromine, right? But don't let that trick you. You could also do SN2 with a CN to do hydrolysis of the CN. You just have to keep in mind the environment, what's present in the molecule already. Yeah. So yeah, I just showed you when to use nitrile, which is when to use a organometallic, which is that one, right? Two sterically hindered substrate for nitrile, acid present here for organometallic. Okay, any questions on the synthesis problem? Right. SN2, hydrolysis of nitrile, and then intramolecular Fischer esterification. Okay, let's move on to the next one. Let's try this. When someone has it, let me know what you guys got or tried to do. Like either retrosynthetically going backwards or going forward. Or a little bit of both and try reading in the middle. Acid, SOCO2, amine, yeah. So organometallic limitation is steric hindrance, right? Yeah. Wait, the limitation for organometallic is acid-base reaction or electrophile. The nitrile limitation is the steric hindrance, right? Because nitrile is trying to do SN2. SN2 doesn't work well with sterically hindered electrophiles. Oxidizing, then acyl halide, then NH. Yeah, so we're gonna hydrolyze this acid into carboxylic acid using acid, water, and heat. That's the first step, right? The next step, SlCO2, that's right, to convert this carboxylic acid into the acyl halide, okay? The most reactive derivative. And then the next step you guys said was the amine, like this ethanamine here, right? Like let's say the excess amount of it. That's gonna give us this right here. This amide, and when we try to reduce it with lithium aluminum hydride acid workup, we are going to get this right here. But there's a problem because there's this carbon that we don't want right there. What reaction can we do to get rid of one carbon?
Hoffman rearrangement.
Yep, Hoffman rearrangement. But there's a very specific amide that Hoffman rearrangement can only react with, which is the primary amide. So we have to do ammonia excess to get that specific amide, primary amide. And then from this primary amide, we do the Hoffman rearrangement reagents, Br2, NaOH, and water to get rid of that carbon and get the amine here. Oh, wait, no, yeah. Minus 1 hydrogen. We substituted this whole amide to this amine right here. We got rid of that carbonyl-carbon. Now, this last reaction here is a little bit tricky, right? Because the ways that you learn how to prepare amines, they mostly make primary amines, right? Primary amine, like Gabriel synthesis, reduction of nitrile or azide, Hoffman rearrangement, what other reactions did you learn to prepare amines? There's reduction of nitrile, reduction of azide, Hoffman rearrangement. Yeah, all of these reactions here, those are going to form a primary amine. But the reactions that could form a primary, secondary, or tertiary amine is going to be reduction of amide or reductive amination. Right. So we see in the products here, we have a secondary amine, and we have a primary amine to begin with. So what I'm thinking is reductive amination, where I'm gonna make a split right here. That was a new bond that was formed, right? Where this was our original amine that we have right here, and this is the carbonyl that we had. So if I dotted that carbon, this is our carbonyl here, which is this aldehyde, and let's say pH of 3 to 4, NABH3CN, right? And that combines this amine with this carbonyl to create this secondary amine here, right? So this was a little bit tricky because when I introduced this to you guys, when you guys learned this, you guys probably seen the carbonyl as the reactant and the amine as the reagent, right? But this is flipping it. The amine here is going to be the reactant and the carbonyl is going to be the reagent, right? So that flips it, which makes this more substituted amine there, right? Where the first step was hydrolysis of nitrile. The second step was acyl halide formation. This one here is amide formation. And then this one here is Hoffman rearrangement. Get rid of one carbon. This is an important reaction, like right here, conceptually and synthetically. Hoffman rearrangement. Right. And then the last is reductive amination. Reductive amination. 1, 2, 3, 4, 5. What is the reaction called? The carbonyl with NABH4. Oh, yeah, so this is NABH3CN, which is a big indicator for reductive amination, which is gonna react a amine with an aldehyde or ketone in basic acidic conditions with NABH3CN to create that other amine there. This is chapter 21 reaction, the beginning of chapter 21, when they teach how to make amines. Yeah. Okay, any questions, guys? How are you guys feeling so far? Like, are you guys getting the hang of it, or?
Makes a lot more sense now. Thank you so much.
Yeah, no problem. I'm glad. It makes a lot more sense. No problem. Yeah. Yeah. Okay. I'm gonna end office hours here, and I'll see you guys maybe tomorrow during the office hours, the last office hours before the midterm one. And good luck.
Brian,
Thank you.
you have an exam tomorrow too, right?
I do.
Good luck.
I know. Thank you.
Yeah, have a good night.
Yeah. Good night. We all got this. Exam season.
Thank you.
Thank you, Brian.
Thank
It's me,
you.
Brooke.
No problem.
Thank you.
Bye.
Bye.
Oh.
Hello.
Hey, Brian.
Long day.
Yeah, long day. Yeah. Wait, I'm gonna go walk my dog, but I'm gonna call you in Discord and we could talk while I'm on my walk with my dog. Is that okay?
Yeah, that's fine.
Yeah. Okay.
I need to charge my phone. It's dead.
Yeah. I'll see you in Discord.
All right.